In this video, we're going to solve this circuit using the node voltage method. So on the left, we have a voltage source. We're going to say it's 70 volts. R1 is 10 ohms. R2 has a value of 5 ohms. And R3 has a value of, let's say, 6 ohms. Now here we have an independent current source with a value of 5 amps. So with this information, how can we use the node voltage method to calculate the current flowing through each resistor as well as the voltage at this point? Now the first thing we're going to do is identify the nodes. So this point right here, we're going to use that node to help us calculate the current in the circuit, as well as this point. Now this is going to be the ground. We're going to use that as our reference node. Now, just to keep things simple, we're going to say that the electric potential of the ground, we're going to assign it a value of 0 volts. So anywhere along this line, we'll have an electric potential of 0. Now, the electric potential at this point has to be 70. Voltage is the potential difference between these 2 points. And based on the source voltage, we know that this has to be a difference of 70. Now, we don't know what the voltage here at that point is. Let's call the electric potential at that point VA. And the electric potential at this point, we'll call it VB. If we can calculate VA and VB, we can figure out the current flowing through each resistor in the circuit. So that's what we're going to try to do. Now, let's briefly review Kirchhoff's current law. So let's say we have a junction. This is basically VA. There's going to be a current that is flowing towards this point, or let's call that point A. Now, because the current is flowing in the junction, this is going to be a positive current. Current flows from a high potential to a low potential. So it's expected that current is going to flow in this direction. Now we do have a current source of 5 amps, which is going in this direction. And likely it's going to go down through this resistor. So we have a current I2 going in this direction. Because that current is leaving the junction, we're going to give it a negative value. I3 is going into the junction, so we're going to give it a positive value. According to Kirchhoff's current law, the sum of the currents must add up to 0. So the equation that we have is I1 minus I2, since it has a negative sign, plus I3, and this is going to add up to 0. So let's get rid of this. Now, according to Ohm's law, we know that the voltage across a resistor is equal to the current times the resistance. Dividing both sides by R, the voltage divided by the resistance is the current. So let's say if we want to calculate I1, that is the current that is flowing through R1. What is the voltage across R1? So V1 over R1 will give us I1. What is the voltage across R1? The voltage is the difference of the electric potentials across that resistor. So it's going to be the higher electric potential. Now, just to review, current always flows from a high electric potential to a low electric potential. So to calculate the current in a resistor, it's going to be VH minus VL. That's the voltage across that resistor divided by R. So in this case, to calculate V1, that's going to be 70 minus VA, because the current is flowing from a potential of 70 volts to an electric potential of VA. The current will always flow from a high electric potential to a low electric potential. It's always going to work out that way. Now we're going to divide this by R1. R1 is 10, and that's going to give us I1. So that's how we're going to calculate the currents in this equation. So let's replace I1 with 70 minus VA over 10. Now what about I2? So that is the current that is flowing through the second resistor. So the voltage across that resistor is the difference in electric potentials of VA and 0 volts. So VA minus 0 is simply VA, divided by the resistance of 5 ohms. Now, for I3, we don't need to use V over R because we already know what the current is. This is an independent current source. It's always going to emit 5 amps of current, regardless of what circuit it's attached to. So I3 is simply 5. So now all we need to do is solve for VA. So let's go ahead and work out the algebra. So the first thing that we're going to do is get rid of the fractions. The highest denominator is 10. And I'm going to multiply both sides by 10 because 10 and 5 can go into 10. So this fraction times 10, the 10s will cancel, giving us 70 minus VA. Now multiplying the second fraction, VA over 5 by 10, 10 divided by 5 is 2. So this is going to be negative 2 VA. Don't forget about the negative sign. And then 5 times 10 is 50. So that's what we have at this point. So now let's combine like terms. 70 plus 50, that's going to add up to 120. And here we have negative VA minus 2 VA. That's like negative 1 minus 2, that's negative 3. Or negative 3 VA. Now I'm going to move this term to the other side. It's a negative on the left side, but it's going to be positive on the right side. So I have 120 is equal to 3 times VA. Dividing both sides by 3. 12 divided by 3 is 4, so 120 divided by 3 is 40. So the electric potential at point A is 40 volts. Now that we know that, we can calculate everything else that we need. So first, let's replace VA with 40 volts. Now let's calculate I1. What is the voltage across I1? We know I1 is going to be V1 over R1. The voltage across R1 is the difference in the electric potential. It's 70 minus 40, which is 30 volts, divided by the resistance itself, which is 10 ohms. So 30 divided by 10, we have a current of 3 amps. So let's put this in blue. Now let's calculate I2. So I2 is going to be the voltage across resistor 2 divided by R2. So that voltage is 40 minus 0, which is 40, divided by R2, which is 5 ohms. 40 divided by 5 is 8 amps. Now we already know the current flowing through R3. That's going to be this current, which is 5 amps. As we can see, this answer makes sense. We have 3 amps flowing from the left, 5 from the right, and that's going to add up to 8, which is consistent with Kirchhoff's current law. Now, how can we determine VB? What is the electric potential at point B? Well, let's go back to Ohm's law. We know that voltage is equal to current times resistance. So we could say that V3 is equal to I3 times R3. So what is V3? Remember, voltage is the difference in the electric potential of 2 points. It's always going to be the high voltage minus the low voltage. Now, looking at I3, I3 flows from point B to point A. So therefore, point B has to be at a higher electric potential than point A. So we could say that VB minus VA is equal to I3 times R3. Now we know that VA is 40. I3 is 5. R3 is 6. 5 times 6 is 30. To solve for VB, we need to add 40 to both sides. So VB is at a higher potential than VA, and its potential is 70 volts. And so that's how we can use the node voltage method to help us to solve for every quantity in a circuit. That's basically it. Now let's work on another example. So here we have an independent current source of 8 amps. Let's say that R1 is 10 ohms. R2 is going to be 5 ohms. And then R3, that's going to have the same value of 5 ohms. Next, we have R4, which is going to be 4 ohms. And then R5, which is going to be 10 ohms. And then the voltage source is 50 volts. Using this information, go ahead and calculate the current in each resistor. So let's identify the nodes. And this is going to be the reference node. That's the ground. Let's give it an electric potential of 0 volts. Let's call this VA. VB, that's the electric potential at point B, and VC. Now the two nodes that we're going to focus on are points B and C. Let's focus on point B. So at this point, we have 3 currents. I1 is going into this node. Because of the 8 amp current, it has to flow in this direction. We also know that I2 is going towards the ground. Now I3, that's going to be a little tricky. Is I3 traveling from point B to point C, or is it going from point C to point B? How can we tell? Because there's 2 different energy sources that will want to push the current in different directions. We have the current source of 8 amps and the voltage source of 50 volts. Now the current source wants to send current through R1 and through R2. Now it can also send current through R3 and through R4. Now the voltage source, I'm going to highlight in red, is going to send a current through R5 and through R4. But it's possible that it could send a current through R3 and through R2, because both of these currents can return in this direction. Now because we have an 8 amp source here, the 50 volt source is not going to send a current through R1. So that's going to be a little unreasonable to think that way. But the real issue is determining the direction of the current in R3. Now you can try to solve this problem by taking a guess, and if you don't get the right answer, you can just use the other direction. That's one way to go, but that's going to take some time. What's the best way in which we can guess the answer? Or is there a method that we can use to predict which direction that this current's going to go? So let's see what's going to happen if we remove R3 from the circuit. If R3 is removed from the circuit, the left side will look like this. And the right side will look like this. In order to determine the direction of the current through R3, we need to determine which value is greater, VB or VC. If VC is greater than VB, the current will flow from a high potential to a low potential. So the red arrow would be correct. If VB is greater than VC, then it's going to flow from left to right. The blue arrow would be correct. And so by taking out R3 and determining the values here, let's call this VB and VC, we can get an idea of which one is going to be greater in this circuit. Now granted, once we remove R3, VB and VC will change. It's not going to be the same as what you see here. But nevertheless, it could give us an idea of which one is larger, and so we'll know what direction the current's going to flow. So let's start with the first circuit on the left. Now we already know the current flowing in this circuit. It's 8 amps. So there's 8 amps of current flowing through the 5 ohm resistor. Now this is going to be the ground with a potential of 0 volts. Using Ohm's law, V equals IR. So we have a current of 8 amps flowing through a 5 ohm resistor. The voltage across that resistor then is going to be 8 times 5, which is 40. So VB is 40. Now, let's focus on the circuit on the right side. We have a 50 volt voltage source, a 10 ohm resistor, and a 4 ohm resistor. Those two resistors are in series. So the total resistance is 14 ohms. We need to calculate the current in the circuit. So using V equals IR, the voltage across those two resistors is 50. And those two resistors add up to 14. So the current in the circuit is going to be 50 divided by 14, which gives us a current of, I'm going to write it here, 3.571 amps. Now the potential here is 0. So if we multiply the resistance by the current, using this same process again, we can get the voltage across that resistor. So 4 times 3.571 gives us a voltage of 14.284 volts. So notice that VB is significantly larger than VC. So therefore, if we add this resistor in this circuit here between points B and C, it stands to reason that VB will still be larger than VC. So therefore, the current will be flowing from point B to point C, from a high potential to a low potential. So let's get rid of this arrow. So now we have everything we need in order to solve this circuit. So let me just clear away a few things. So focusing on point B, current 1 is flowing towards that node, so we're going to give it a positive value. Current 2 is flowing away from it, so we're going to give it a negative value. And I3, that's flowing through resistor 3, that's flowing away from point B. So we're going to give that a negative value. So the equation that we have is positive I1 minus I2 minus I3 equals 0. So remember, the current is going to be the high voltage, or rather, the high electric potential minus the low electric potential divided by the resistor. So I1 is going to be, it's flowing from A to B, so VA is larger than VB, as you can see, divided by R1. We don't know what VA is, nor do we know the value of VB. Actually, we already know what I1 is, so we really don't need to do this. I1 is given to us, that's 8 amps. That'll make this a whole lot easier. Now, for I2, we do need to use that formula. So, it's going to be minus. The high potential is VB, the low potential is the ground, that's across R2. So VB minus 0 is just VB, divided by R2, which is 5. And then I3, so for I3, it's traveling from point B to point C, if you follow the direction of the arrow. So it's going to be VB minus VC divided by R3. So let's put that in parentheses. VB, we don't know the value of that, nor do we know the value of VC. R3 is equal to 5. So this is one equation that we have so far. Now let's simplify this equation. Let's multiply every term in this equation by 5. So we have 8 times 5, which is 40. And then this fraction times 5. The 5's will cancel, giving us negative VB. And then this fraction times 5. The 5's will cancel again, giving us negative VB minus VC. And 0 times 5 is still 0. So now let's distribute the negative sign. So this is going to be 40 minus VB again, and then plus VC. Now let's combine like terms. Negative VB minus VB, that's negative 2VB. And then we have plus VC. I'm going to take the 40, which is positive on the left side. I'm going to move it to the right side, where it's going to be negative 40. Because what we're going to have is a system of equations. So using node B, we were able to write this equation. Now let's do something similar, but with node C. So we have I3 flowing towards node C. I4 is going away from it, so that's going to have a negative value. And I5 is going towards node C, so that's going to have a positive value. So I3 and I5, they're going towards point C. They're positive. I4 is moving away. It's negative. So the equation that we're going to write is I3 minus I4 plus I5, which is equal to 0. Now, what's I3? So I3 flows from point B to point C. So it's going to be the voltage, which is VB minus VC, divided by R3, and R3 is 5. Now I4, the voltage across that is VC minus 0. So that's just going to be VC. And then divided by R4, which is 4. I5, now if this is 0 volts, anywhere along this line is going to be 0. Here, this has to be 50 volts. And the current flows from the 50 volt potential to a potential of VC. So 50V is higher than VC. So I5 is going to be 50 minus VC divided by R5, which is 10. And that is equal to 0. So to get rid of the fractions, we're going to multiply both sides by 40. 40 is the least common multiple of 4, 5, and 10. Actually, no, 20 is. 20 is a better number. 5, 4, and 10 can all go into 20. So let's multiply every fraction by 20. So this fraction times 20, what's the answer? The best thing is to divide first. 20 divided by 5 is 4. So this is going to be 4 times VB minus VC. Now let's multiply this by 20. 20 divided by 4 is 5. So this is going to be minus 5 VC. And then 20 divided by 10 is 2. So we're going to have plus 2 times 50 minus VC, and that's equal to 0. Now let's distribute the 4. So we're going to have 4 VB minus 4 VC minus 5 VC. And then 2 times 50 minus VC, that's going to be 2 times 50, which is 100. And then minus 2 VC, and that's equal to 0. Not sure what just happened there. Let's do that again. Now let's combine like terms. So we can combine these three. So we're going to have 4 VB, negative 4 minus 5 minus 2, that's negative 11. And then the 100, I'm going to move it to this side, where it's going to be negative 100. So notice that I've aligned VB and VC in such a way that I can solve those systems of equations using the elimination method. So I'm going to focus on canceling VB. I'm going to multiply this equation by 2. The other equation, I'm just going to rewrite it for now. Notice that I have positive 4 VB in the first equation. If I multiply this one by 2, I'm going to get negative 4 VB. So when I add these two equations, VB will cancel. So let's go ahead and do that. Negative 11 plus 2, that's going to be negative 9. And negative 100 minus 80, that's negative 180. Our next step is to divide both sides by negative 9. Now, 18 divided by 9 is 2. So 180 divided by 9 is 20. We just got to add the 0. So VC is 20 volts. Now let's calculate VB. I'm going to use this equation before I multiply it by 2. So I have negative 2 VB, and let's replace VC with 20. And now let's subtract both sides by 20. So I'm going to have negative 2 VB equals negative 40 minus 20, which is negative 60. Now let's divide both sides by negative 2. Negative 60 divided by negative 2 is 30. So VB is 30. With VB and VC, we can now calculate every current in this circuit. We can even calculate VA as well. So remember these values. I'm going to erase the board and draw a bigger circuit so that we can place all of these values in this one circuit. Now let's continue where we left off. So this is 0. We know this is 50 volts. And we said that VB was 30 and VC was 20. So as we predicted, notice that VB is larger than the VC. So current is definitely going to flow from point B to C in this direction. Now let's calculate the currents. And let's calculate VA as well. Now we have 8 amps of current flowing through R1. So what is the voltage at point A? We know that V is equal to IR, where I is going to be I1, R is R1, and the voltage across that resistor going from a high potential to a low potential following the direction of the current, it's VA minus 30. I1 we know it's 8, R1 is 10. 8 times 10, that's 80. So adding 30 to both sides, we can see that VA is 110. Now let's calculate I2, which we know it's flowing in this direction. So V equals IR. I is going to be V over R. The voltage across resistor 2 is going to be the high electric potential minus the low electric potential divided by the resistance. So this current flows from a potential of 30 volts to a potential of 0. So that's going to be 30 minus 0 divided by R2, which has a value of 5 ohms. So 30 over 5 is 6. So we have 6 amps of current flowing through resistor 2. Now let's calculate I3 using the same formula. VH minus VL over R3. So I3 flows from a potential of 30 volts to a potential of 20. So this is going to be 30 minus 20 divided by R3, which is 5. 30 minus 20 is 10. 10 divided by 5 is 2. So R3 is 2 amps. Now, does that answer make sense? Let's analyze the situation using Kirchhoff's current law. We have 8 amps of current flowing through point B, or towards point B. 6 amps is going down, 2 is going towards the right. So we have 8 amps of current entering that junction and 8 amps of current leaving that junction. The amount of current that flows to a point should equal the same amount of current that leaves that point. So right now the numbers are making sense, which means we are on the right track. Now let's calculate the next current. Let's calculate I4. So this current flows from a potential of 20 volts to a potential of 0 volts. So that's going to be 20 minus 0, and the resistance is 4 ohms. So 20 divided by 4 is 5. So we have 5 amps of current flowing through R4. Now let's do the same thing for I5, the current that flows through this resistor. So I5 is going to equal the high potential minus the low potential. So that's going to be 50 minus 20 divided by R5, which is 10. 50 minus 20 is 30. 30 divided by 10 is 3. So we have a current of 3 amps flowing through this resistor. Now, does that answer make sense? So notice that we have a 2 amp current flowing towards point C and a 3 amp current flowing in that same direction. 2 plus 3 is 5. And so it makes sense that 5 amps will be leaving point C. So right now, everything makes sense. And so we've basically solved the circuit. We know all the currents in the circuit, and we know the electric potential at each point in the circuit. So that's basically it for this problem.